Swayam Prabha. Digital India. Educated India.
Welcome back. In lecture 59, we will continue with geospatial analysis, and this is part 2 of this lecture series. So the different concepts that we will cover in this lecture will be on hotspot analysis, cluster and outlier analysis, space-time analysis, geospatial analysis, 3D analysis, spatial modeling and analysis tools for raster data, and then we will also talk about imagery analysis. Now, coming to hotspot analysis, which is otherwise done through this statistics, which is known as Getty's ORD GI star. This is not the purpose of this particular analysis is to identify the hotspots, right, which are the areas where some certain feature value is very high or either it is very low, right. But it is not estimated for directly, like if it's just a high value, then we don't call it that it's a hotspot. What we do is, if the high value feature is statistically significant, then only we will call it as a hotspot, right. So what it means is, that means this is also some similarity with clustering that we have learnt earlier during machine learning lectures. We have discussed about how to divide the data set into different parts where we can identify which are the high values or the low values, and we can or different groups of values. So it has got some analogy with clustering, but this is not exactly clustering. Here we are proposing a new statistics, which is a spatial statistics, you can say, and this is used for identifying statistically significant spatial locations which are either high or low based on the value of a certain feature. So what is a statistically significant hotspot? A feature with high value and surrounded by other features with high value. For example, we are talking about crime, number of crimes that is happening in an area, or crime rate. So we will identify a particular ward as high if that particular ward has got a high value and also surrounded by other other wards of higher value. So then only that becomes a hotspot, right? Otherwise, one particular ward may have a higher value, right? So and then the next plot may be a lower value, but we cannot call it a hotspot. That means in this area we are seeing higher values compared to other areas. So what we do is, we take the local sum for a feature and its neighbor, and it is compared proportionally to the sum of all the features. Feature means that particular attribute that we are talking about. And if the difference is too large and not a result of random chance, that is, we have to bring in the concept of z-score, and utilizing that we could say that based on the value z-score value, it is either significant or not, and then we can call it either the features are having low value or high value, or these are high or low value clusters which are spatially we can mark them on a particular map. So in addition to that, for this particular analysis, FDR or false discovery rate correction is also applied. So we have talked about that in some lecture earlier. So this is the statistics that we get. So what we get here is basically this GI star compares the local weighted sum of neighboring values with the global average, and standardizes it to identify statistically significant hotspot and cold spot. Now, because we are standardizing it, we are getting a value which is like a z-score, and then based on the variance, we can determine at what level or what value we can call it at a high or a low, and vice versa. So this GI star is basically Getty's ORD GI star statistic, which could be otherwise its form of a z-score, you can say. Then xj is the value at location j. Wij is the spatial weight between location I and j. Now this is very important. Now why it is important? Now this actually determines how many nearby locations we are considering. That means if Wij value is 1, that means that is if 1 if it's a neighbor, or we can say 0 if it is not. So what we can say, that suppose I have got a particular cell, I can say all the cells which are neighbor, I am giving it a value of 0, and then it is given a value of 1, everything else is given a value of 0. So in that way we can choose neighbor. or it would be based on some distance based weight. That means we can say that something like, so many within a distance of so much, all would be considered as neighbors, right? So we can determine what is the neighborhood using this particular, a particular spatial weight, and n is the total number of locations that we are considering. Now, how does it look in map? Eventually, when we are talking about a z-score value, of course, it comes with a p-value. So that is where we can tell it if it is significant or not. And so this is where you can see the statistics after being computed. We can compute what is a 2SD, 3SD, and so on. And from there, we can take a call on what is a hotspot or cold spot. So the hotspot is basically statistically significant positive z-scores. Larger the z-score, more intense is the clustering. Cold spot is statistically significant negative z-score. So smaller the z-score, more intense is the clustering. So this is how we can identify, generally, hotspot or cold spots that is happening maybe in an urban area. Now, the next thing that we need to understand is a lot of these data points that we are talking about are all point data. That means, suppose incidents of crime, we are marking those locations on the map, or we are finding locations of accident. Then, or we are talking about say something like incidents of fire, right? So all these are point data, right? So we can create a fishnet tool which is like a polygon grid over the point features, and then we can use spatial join to determine how many points fall within that fishnet tool, and that becomes the value of that particular fishnet tool. So that means that we are creating this polygon feature, and the spatial join will allow us to count the number of events that is happening within that particular polygon feature. And so otherwise we can say that incidence data becomes segregated, and then we are trying to find out which are hotspot or cold spot. Now, why we need to do this? Maybe we could do it as per each ward, or as per each state, or as per each county. But the problem is sometimes, if we take into, a very large set of data areas, then probably the values may not be clear. So instead, we divide the area as per our understanding. We do grids of some form, and then we can understand which zones in the city we are having some crime hotspot or some other forms of hotspot. So this is the next thing is, of course, we have to think about the distance band. That means what is the distance within which we are considering a particular features to be neighbors or not, or incidence points to be neighbors or not. So it could be a fixed distance band. All locations within a fixed distance could be considered as neighbors, and then we can say that if distance is lesser than equal to d, it is 1. If distance is greater than equal to d, then it is 0, right? So that's the WH is the distance between I and j. So from there we can take a call if it is a neighbor or not. Then it could be based on spatial autocorrelation, that means particularly by distance, of course. So we choose the distance where clustering is most intense. So based on the spread of the data, we can see at what level clustering is happening, and we can choose that particular distance. Or it could be based on contiguity. That means what is adjacent to each other, like we were drawing one particular cell. So what is adjacent to each other, based on that we can also say this is a neighbor or not. So rook's case, queen's case, this comes from chess. So queen's case is queen can go in all directions, so all the points surrounding. Rook's case is it can only go in certain direction, not in the diagonals, only in the straight lines. So only those would be considered as neighbors. So these are the two ways we can consider neighbors. Then it could be based on the k nearest neighbor, that is the k value, the k cells which are near within that particular distance, those would be considered. Then it could be sometimes this could be not a regular cell, right? So this could be ward boundary. So in that, whichever falls within that k, whichever are the k nearest neighbor, those would be considered. Then network spatial weights, that means we can measure the distance in different other ways as well. So over here you can see in this particular map, this is where this is just an illustration that a fishnet tool has been created. Then we have run the program, and you can see the hotspots and cold spot. Red is intense hotspot, deep blue is intense cold spot, grayish is lesser value of cold spot, light orange is lesser value of hotspot, and the rest are neither hotspot neither cold spot. So this is where we have tried it using the data sets available in ESRI. So this here you can see the New York State data set, and there you can see the what we have used is the median home value in those particular states, and we are trying to see that where the values are higher, or which areas are forming a hotspot. So obviously this side is most likely New York. So we are seeing that this area is having lot of hotspot in this particular area. So we didn't find any cold spot over in this particular map, but we did find very intense hotspot with 99% confidence we can say those are hotspot, and then there are orange spots where we can also say that the confidence is high, but these are also some form of class hotspot you can say. So you can see that we are giving output feature class as well over here, and we have considered here contiguity edge corners instead of some KNN or something else, right? K nearest neighbors or so on. So once we run, so we get the values of this particular get is ORD GI star, and that is actually also, and the what is the value, that is also being illustrated here. Next we will do something similar, but here we use a different statistics, which is Anselin local Moran-Sai. So that is known. So here what we are doing is we are doing both a cluster and outlier analysis. So we are not only interested to know which are the high value clusters or the low value clusters, but we are also trying to understand that if there are outliers as well. That means there is a low value, but it is in presence of all high values, or if it is everything is high value, one value is a low value, right? So that becomes an outlier. So that is also very interesting in urban planning, because you need to sometimes understand that within suppose in an affluent area suddenly we find that one area is not that affluent, right? So what are the reasons for that? So then we can go there and find out what is the reason, or in some area out of the entire area in the city only one or two spots, and those are outliers, that is where we are finding crime. So we can then further investigate what is the reason for that. So cluster and outlier analysis, or otherwise known as Anselin Moran-Sai, is a local spatial statistical method. So again, these are not exactly machine learning, but there is a lot of similarity with machine learning, clustering and other things, but these are spatial statistics, and in this case it measures local spatial autocorrelation. So sometimes students make a mistake between autocorrelation and correlation, right? Spatial autocorrelation and correlation. So this is actually talking about in the spatial context, which things nearby are showing similar values or so on. So it's a local statistical method which identifies clusters and spatial outliers by comparing a location's value with its neighbors. And unlike GI star, only hotspot and which shows hotspots and cold spots, this also detects outliers. That means where mismatch is happening with the neighbors, and it measures how similar locations value to its neighbors by comparing deviation from the mean. So this is the Anselin local Moran-Sai statistic, where you can see that we have taken xi minus x bar. Xi is the value at location I, x bar is the mean of all values that is there, and then over in this side you can see this is xj minus xj is the other value of neighboring locations j, and we are taking again we are subtracting the value of x bar from over here and then multiplying with wij and then taking a summation, so that we understand that okay depending on what is the number of neighbors, and then the average of those is taken. The difference between from the different deviation from the mean is also taken for the neighbors as well, right? And then we also divided by over here xk minus x bar whole square divided by n. So this is where we are also so n is the total number of locations. So we all, based on the value of I1, we compute the z score and the p values to measure statistical significance. So that means again we will get a value of I, and then we can using we are standardizing, so we can understand that okay at what are the using the same concept as z score, using the concept of z score we will also try to determine which are beyond 1 SD or 2 SD, and accordingly we can say which is hotspot or cold spot. So CO is cluster outlier type analysis, where this HH is statistically significant cluster of high values. LL is statistically significant cluster of low values, and if the negative z, if the value has got low negative z score less than minus 3.96, right? So for a feature indicates statistically significant spatial data outlier. So what we are seeing over here is the entire the data gets divided into 4 quadrants. So these are feature, if the feature is higher than other features, neighborhood is lower than other neighborhoods, then it is a high-low out. This is a high-low mix of high and low value areas, so it's a outlier. Whereas if it's a feature is higher than other features, neighborhood is higher than other neighborhoods, then it's a high-high cluster. Then similarly we have a low-low cluster, and where feature is lower than other features and neighborhood is also lower than other neighborhoods, then it's a low-low cluster. But again here we find outlier where feature is lower than other features and neighborhood is higher than other neighborhoods, right? So this is actually a way to measure dissimilarity, right? So that's why we are bringing in Morans. So this is where we have applied that, and you can see over here that we have used the same data set. That means the median home value in New York is being considered, and then the output feature class is given. Again we are taking contiguity edge corners, and we are standardizing also, and then you can see over here this is the value that we are getting. So high clusters, high-low outliers, then low-high outliers, and all these things are marked accordingly. These are identified. But if you again I will So to some extent what we were discussing right now, you can see over here, this is a little different analysis, but we can understand within a particular area, if you suddenly find something as red within a set of blues, or within a set of reds, within a set of blues you find a red, then automatically those are outliers, right? Now here in this particular analysis, what we are doing is we are doing space-time analysis, and for that we are using space-time pattern mining tools such as we can do different sorts of analysis such as emerging hotspot, local outlier analysis, time series clustering, space-time cube in 2D and 3D, and these are some of those listed over here. Now over here you can see this is something where we are doing a emerging hotspot analysis. Now what is emerging hotspot analysis? So that means it is currently an hotspot, but it was a hotspot, now it is not, or it's being a hotspot for a long time. So these all things we can measure. So that means if we have time series data, we can check if it was a hotspot or an outlier earlier, or if it was a hotspot earlier, and based on the different time periods we can see if that particular area is changing. For example, if you have a very dark red over here, that means it's a new hotspot. If it's a little bit less reddish, then it's a consecutive hotspot, that is twice it is being a hotspot. Then intensifying hotspot means gradually it is becoming more hotter. Persistent hotspot means it's always been a hotspot. Diminishing hotspot means earlier it was a hotspot, now getting lessened. So in this way you can get new cold spot, intensifying cold spot, persistent cold spot, oscillating cold spot, sporadic cold spot, historical cold spot. So we can see how a particular area is changing in regards to that. So that means if there is crime and I have taken some measures to reduce it, so we can check if it is really having any effect using this particular analysis. In addition to that, we can also do general time series clustering or space type cubes and so on, that we will discuss. So this is the illustration of a space-time cube. That means that we have 3 axes, x, y, and then there is the z axis or the time axis, right? So that's why it is given, a time piece is given. So that means we have these bins. That means in a 3D space, we have each bin contains the data, right? Some bins may have 1, some bins may have 2. So similar to the fishnet tool, I can use this binning to determine how many things are there in that particular bin, and I can take the average value of that. So it could be like sensor data, that is coming, that is being recorded. So depending on the locations of sensors, we are getting the data for air pollution maybe, right? So you can see that this could be a grid of 10 by 10 kilometers. That's the XY grid, and then this could be the monthly data. So whatever sensors are there within this particular grid, I can take the average values of that, and I'm getting to store the data, right? And eventually we will get a space-time cubes which looks like this, and the colors actually tells us that, well, it is higher than the other higher than the that value is a hot spot or a cold spot or so on. So sometimes some of the values are empty. Now there are some strategies to fill up the empty bins, which is key while doing this kind of analysis, because we cannot have empty bins as such. So it could be based on the spatial neighbor, so I can take an average of all the values surrounding it, or it could be a space-time neighbor. I can take a space-time cube and take an average and fill it there. So we are doing temporal aggregation here, and then temporal neighbors in time series. So here, instead of taking average, I can also use a time series, or I can predict that, okay, this is how this particular spot is changing, and accordingly I can determine the current value. So for spatial aggregation, we use fishnet grid, hexagon grid, and so on. For temporal aggregation, each sensor could be put inside a bin, and this is how we can analyze the data further. So when we do this space-type analysis, what we use, you can use this where you can create a space-time cube from defined location. So we put in the input features, the output space-time cube, and then for what are the different tables that we are taking in, and once we have done that, we have specified what are the input values, then we can analyze the value in regards to the same, we are trying to analyze poverty over here. So this actually tells us that how the value is changing over time, right? So that means, is it increasing or is it decreasing? So you see, these are the ones which have remained same as it is. Now over here the amount has got increased. So we can take certain, based on this data, we can make certain decisions about what to do about those particular areas, right? So in addition to this kind of analysis, we can do many other analysis in ArcGIS. So I will just summarize some of this analysis. And for example, we can do geostatistical analysis. It involves analyzing spatial data such as points, lines, rasters to understand patterns, relationship, and then make predictions, right? So some of the tools for performing deterministic and geospatial interpolation could be like exploratory spatial data analysis, kriging, sampling and simulation. Interpolation could be also done in 3D and so on. So usually what happens, we get data for different areas, right? But we are always taking a sample data. We cannot cover an entire area, or we may not have got sensors in entire area, right? Or we have not conducted services in entire area. So one idea is to represent the data. Of course, we can use different colors to represent the values, and we can understand how clusters are forming and so on. But the other thing is to predict something. That is, okay, I don't know the value for this area, I don't know the value for this area, what would be the likely value, right? So there has to be some statistical procedures to see what could be the likely value for this particular area, right? So this is known as the process of interpolation. So interpolation estimates values at unknown location using known sample data points. I have not given the equations here, but and there are different ways we can do that based on different thought process, that how we are thinking about this, is it the average value between 2 points and then we extend that. So there could be different ways of doing that. So kriging is an advanced interpolation technique that predicts values using spatial autocorrelation and statistical modeling. So these are the different things, and from there we can see this kind of, we can do this kind of prediction maps. That means even though I may not have a data point here, but I may be able to say that what is the likely value, expected value over there for this particular, say this is air pollution related with CO2 emission, right? So air pollution from dust, from particulate matter, right? So using this, this is very important for many environmental analysis and so on, like air pollution mapping, noise level estimation, traffic density surfaces, urban heat island analysis, land value mapping. All this we can use this kind of kriging or interpolation to find out or fill up the values where we have none. So in addition, you can do so many other things. You can explore this using the softwares. Again, we are talking about ArcGIS. It's a commercially available software. It's quite costly as well, but it has got an extraordinary number of tools, Many of that is also available in freely available software such as QGIS and all, but not everything. So we are doing this so that you get to know the idea about how many different kinds of analysis could be done. Then of course, if that could be done in QGIS or free platforms, that would be obviously better. We can also do 3D analysis. For that, we use the 3D analyst tool. So this version of the software is a bit older. So now we have got other features also coming up. So gradually the company keeps on adding features and all. So it is used for 3D analysis. It is used for doing many things, for working with digital elevation models. We can generate surface models. We can do 3D vector, use 3D vector data. We can develop 3D feature relationships, data interpolation, data management, surface generation, visibility. We can use leader data. We can see the leader data. Then you can use city engine, and we can give textures to different buildings and so on. So for example, you can see sight lines. We can check if sight lines are available. Then we can see what is the sky view available for a particular location. Then we can create 3D buffers. Like for example, a metro line is being constructed, and we are creating a 3D buffer to see how many trees needs to be cut down. Then we can do volumetric analysis, that what amount of water would be held in this particular terrain, or based on the slope and the flow patterns, right? So these are the different things that we can do in 3D analysis. We can do a lot of spatial modeling and as well, and for that we can use raster data as well. So you can see the list of things that we can do over here, and we can do overlays. We can do multivariate analysis, and we can develop surfaces. And so spatial analyst is an extension in ArcGIS Pro used for raster based spatial analysis and modeling. So it provides tools for overlay analysis, distance analysis, surface terrain analysis, hydrological modeling, and suitability modeling. It also supports map algebra, raster calculations, and spatial interpolation for advanced decision making. So over here you can see that we are using several layers: distance from road, solar radiation, slope, aspect, elevation, and we are trying to see which are the areas which will satisfy, which is not based on the criteria that we said. We can extract certain area which will satisfy all the different criteria that we have set for each of these layers. So we can do a lot of suitability analysis over here. That is, we identifying a suitable surface for purpose by combining maps of different attributes to support decision making, and this is called suitability analysis for multi-criteria evaluation in GIS. So this is one way to do that. And we can also do other things like watershed analysis with digital elevation models, and then we can do suitability modeling as well. So it's not only just putting layer and all, but also we can do some form of prediction as well. Then we can also do imagery analysis as well. So this over here we can do, it is an extension used for analyzing satellite and raster imagery, of course, and it supports image classification, deep learning, change detection, stereo mapping, multidimensional analysis, and so on. And it also provides raster functions and tools for real-time processing and feature extraction for imagery. So you can see that we can use deep learning over here to identify certain features. We can do image classifications, and we can do stereo mapping from the data that we can generate height value and other values from a satellite, from a photographs which is taken from say a airplane, and then we can do multidimensional analysis, and that using that we can do a lot of this environmental maps and so on. So these are the different sorts of analysis that we can do. And of course, we can do many things more, but this is just to give you an idea about what are the things that is possible to do in this kind of GIS softwares. So these are some of the references you can use, and you can use this ESRI documentation where you will see most of these are covered. And to conclude, geospatial analysis provides powerful tools to understand spatial patterns, relationship, and processes by integrating statistical methods, spatial modeling, and computational techniques. Thank you.